Hello everyone. Today we're going to discuss the combined gas law. So we learned about how pressure, temperature, and volume are all related to each other, and now we're going to put all of those relationships into one single law. All right, so again, here's a summary of the gas laws that we've covered so far. So table 8.6 goes over Boyle's law, Charles's law, and Gay-Lussac's law. Now, the combined gas law is P1 V1 over T1, which is equal to P2 V2 over T2. So we took all of the laws that we already learned, where P1 V1 is equal to P2 V2, V1 T1 is equal to V2 over T2, and P1 over T1 is equal to P2 over T2. So we just kind of combined all of these different relationships into one law. Now, what's really great about the combined gas law is, let's say you're given a problem and you're only given pressure and volume. That means you can just ignore temperature, and then that gives you Boyle's law. Or let's say you're only given volume and temperature, then you can just cancel out pressure because it's constant, or we can assume it's constant. And that would give you Charles's law. And again, if you're given pressure and temperature but not volume, you can cancel out volume, and that will give you Gay-Lussac's law. So the combined gas law can be a little bit easier to digest or remember than all of those individual gas laws. Now, in this law, we're also assuming that the amount of the gas does not change. So we're assuming we have just a simple collection of atoms or particles, and we're only changing the pressure, the volume, or the temperature. All right, so let's use the combined gas law. So let's say a gas has a volume of 675 milliliters at 35 degrees Celsius and 646 millimeters of mercury. What is the volume in milliliters? At negative 95 degrees Celsius and a pressure of 802 millimeters of mercury. And again, the amount of the gas stays constant. Okay, so we've been given a lot of information. So I'm just going to write down, let's see, P1, V1, T1, P2, V2, T2, since those are all of the variables in the combined gas law. All right, now I'm going to just identify which one is which. So we're given an initial volume, V1, of 675 milliliters. We're given our initial temperature of 35 degrees Celsius and our initial pressure of 646 millimeters of mercury. All right, and then P2 is 802 millimeters of mercury. And then we don't know what the new volume is, so that will be a question mark. And then T2 is negative 95 degrees Celsius. Whew, that's a lot. Okay, now first things first, remember everything has to be in Kelvin for temperature. So let's just add 273 real quick to each of our temperatures. And this is a really good example of why we have to use Kelvin, because we're given a negative temperature value in Celsius. And if we use that value, we're going to end up with a negative volume, which isn't possible in this scenario. So we definitely want to use Kelvin. All right, so let's figure out our new temperatures in Kelvin. So for T1, I get 308 Kelvin. And for T2, I get 178 Kelvin. Okay, so now we're just going to plug all of these values into the combined gas law. Okay, so I'm just going to start writing these in. I'm going to use a different color so we don't get confused here. Let's see, so we have 646 times 675 all over 308 Kelvin. And then that's equal to 802 millimeters mercury times our unknown variable, V2, divided by 178 Kelvin. Okay, so I'm going to simplify this a little bit. I think I'm going to solve for the left side and then the right side. That might make it a little bit easier. So let's see. So solving for the left-hand side, we have 646 times 675 divided by 308. Okay, so I get 1,415.7, and I'll just leave it there for now. And then I have a bunch of units here. So I've got millimeters of mercury times milliliters over Kelvin. And then the right-hand side I'm going to solve for. So 802 divided by 178. That gives me 4.5. And then that's times V2. Okay, so now I'm going to divide both sides by 4.5. Okay, so 4.5 will cancel on the right-hand side. And on the left-hand side, we have millimeters of mercury, which will cancel, and then Kelvin, which will cancel. So we're left with milliliters. All right, so let's figure out what V2 is equal to. So 1,415.7 divided by 4.5. And let's see, I'm going to make some room up at the top for our answer. Okay, so that gives me that V2 is equal to 315, and the final unit is milliliters. And I left this at 3 sig figs because all of my original values had 3 sig figs. Okay. Great. So not too bad, pretty similar to all of the previous problems we've done, but this time we just have all of our variables in one place. And here are the solution slides. So I kind of lied to you. We have one more gas law, which is called Avogadro's law. And Avogadro's law incorporates moles into our different relationships. So this one relates volume to moles. So in Avogadro's law, the volume of a gas is directly related to the number of moles of a gas. So volume is directly related to the amount of gas. So for instance, on the right-hand side, we have a figure showing 6 particles of gas in a container. And let's say that that's equivalent to 1 mole of a gas. And then let's say in this condition, we have a volume of 1 liter. Now, if we add more gas to this system, so let's say we double the amount of gas to 2 moles, the volume is also going to double. So that's going to double to 2 liters. And that's really just to make space for the new particles of gas that have been added to the container. So as volume increases, or I guess as the amount of gas increases, the volume increases. If the amount of gas decreases, the volume also decreases. So our equation is very similar to both Charles's law and Gay-Lussac's law, but this time we have volume and amount. So V1 over N1 is equal to V2 over N2, and this is assuming that temperature and pressure are constant. So let's just do a quick practice problem using Avogadro's law. So if 0.75 moles of helium gas occupies a volume of 1.5 liters, what volume will 1.2 moles of helium occupy at the same temperature and pressure? And then we're given three options down below. Okay, so let's write out what we're given. So we have an initial amount, N1, that's equal to 0.75 moles. And then we have our initial volume of 1.5 liters. Our new amount of moles is 1.2, and then we don't know what V2 is. Okay. All right, so let's just plug those values into our equation. Oh, N2. All right, so we've got 1.5 liters for V1, and we're going to divide that by 0.75 moles. And then that will equal V2, our unknown variable, over N2, which is 1.2 moles. All right, so now let's multiply both sides by 1.2. So moles will cancel on the right, and then they'll cancel on the left. So we'll end up with liters, which is what we want. That's a unit of volume. All right, so 1.2 times 1.5 divided by 0.75. That should give us a volume of 2.4 liters. And everything does have 2 sig figs, so I'll leave my answer with 2 sig figs. And this also matches answer C. All right, so again, this is very similar to Charles's law and Gay-Lussac's law, so we've seen this before. Now, the reason that this is important is due to something called STP, or standard temperature and pressure. So what's really interesting is that we can compare the volumes of gases at standard temperature and pressure when they have the same temperature, and that temperature is going to be what's called the standard temperature of 0 degrees Celsius, or 273 Kelvin, and when they have the same pressure, which is going to be a standard pressure of 1 atmosphere, or 760 millimeters of mercury. So this is a really cool fact about gases. If those, let's say you have different samples of gases, and they're at the same temperature and the same pressure, you can directly compare their volumes. So at standard temperature and pressure, or STP, 1 mole of a gas occupies a volume of 22.4 liters. And this is called its molar volume. So what this is saying is if you have, let's say, nitrogen gas, so 1 mole of N2 at 0 degrees Celsius and 1 atmosphere, that is going to have a volume equal to 22.4 liters. Now, that's going to be true for any gas. So that could be 1 mole of oxygen, and the same thing would be true. Or maybe it's 1 mole of CO2 at 0 degrees Celsius in 1 atmosphere. It will also have a volume of 22.4 liters. So this is a really cool fact about gases. Now, we can write this as an equality where 1 mole of a gas is equal to 22.4 liters at STP. And so we can convert that into conversion factors. So we could put 1 mole in the numerator or in the denominator, just depending on what we're solving for. So this figure really highlights the same thing I just went over. So let's say we have helium in a balloon, oxygen in a different balloon, and then nitrogen in yet a different balloon. And let's say that all of these gases are at 273 Kelvin, which is standard temperature, and 1 atmosphere, which is standard pressure. So even though all of these gases have different molar masses, remember gases and their particles are really spread out, and the volume that they occupy is a lot larger than the volume of the gas itself. So the mass here doesn't even really matter. It's really just the amount in terms of moles. So we have 1 mole of each gas at this temperature and pressure. So they're all going to have the same exact volume of 22.4 liters. Okay, and Avogadro's law is related to this as well. So earlier we said that volume is proportional to the amount of the gas, and this is proving that as well. So let's use that molar volume equality where 1 mole is equal to 22.4 liters at 273 Kelvin and 1 atmosphere, or STP. So what is the volume occupied by 2.75 moles of nitrogen gas at STP, so standard temperature and pressure? Okay, so if we're at standard temperature and pressure, I know that I can use the molar volume as a conversion factor. So I'm just going to set this up where 2.75 moles of nitrogen is just being converted to liters. So I'm going to use that equality up above. So I'm going to put 22.4 liters in the numerator, and I'm going to put 1 mole in the denominator to cancel it out. Okay, so moles will cancel, and we'll be left with liters. All right, so according to my calculator, oops, our volume is going to be 61.6 liters. So this is a really simple way to convert between moles and volume if you are at standard temperature and pressure. Instead of having to plug everything into the combined gas law or Avogadro's law, for instance. So you can just use this as a simple conversion. Okay. All right, so next time we're going to talk about our final gas law. And this time it really is our final gas law. This one is called the ideal gas law. And this is going to combine pressure, temperature, volume, and amount of gas. So we're going to really use all of the different variables in one law. So I will see you then.